Very good morning to all of you. We will continue with our discussion in electrostatics. Let us recall, in the last lecture we had discussed about capacitors and capacitance. So, capacitors are made up of two conductors separated by air or by an insulator, and they carry equal and opposite charges. So, plus q and minus q, and this particular device is called the capacitor, and it stores charges, and it actually stores electrostatic energy. We had calculated the capacitance of a parallel plate capacitor, a cylindrical capacitor, and a spherical capacitor. So, today what I want to do is to calculate how much energy is stored in a capacitor. So, the topic today is electrostatic energy stored in a capacitor. So, as before, I have two conductors, one carrying charge plus q, the other carrying charge minus q, equal and opposite charges. There are electric field lines between these charges, and we start with two conductors which have no excess charge, and we slowly move charges between the two conductors, so that one of them gets positively charged, the other gets negatively charged. So, we are moving electrons from here into this conductor to leave positive charge here and an excess negative charge here, and this process is called charging the capacitor. So, the capacitor is connected to a battery, and that battery charges the capacitor. So, the question is, when I charge the capacitor, how much energy is stored in the capacitor? So, to calculate this, let us follow the following procedure. So, suppose at the end we have a charge plus q and minus q, and charge is q and potential difference V, and we know that q is equal to C times V, where C is the capacitance. So, now I start with a pair of conductors which are neutral and no excess charge. Now, as I start to move electrons from this conductor to this conductor, I start doing work, because the electrons are being pulled by the conductor here, and I have to move the electrons away from its force. So, for moving the electrons from here to here, I must do charge, and that is the energy which is stored in the capacitor. So, let me assume that at some instant of time the charge is q and the potential is given by V is equal to q by C, where C is the capacitance. So, at some instant of time there is a charge plus small q and minus small q on the two conductors. They have a potential difference given by V is equal to q by C, where C is the capacitance. Now, at this point, to further increase the charge, I move a small infinitesimal charge dq from one conductor to the other conductor. So, I move an infinitesimal charge dq, and because the potential is V, the work done in moving charge dq will be V times dq, which is equal to q dq by C. So, I have replaced the potential difference between the two conductors by q by C, and I get this. So, I start with two conductors with 0 charges and keep on moving charge from one to the other to finally charge the capacitor to a plus q and a minus q, and so the total work done in charging from 0 to capital Q will be W is equal to 0 to q by C dq, which is equal to 1 by C integral 0 to q dq, which is nothing but q square by 2c. So, the external agent has to do a work amounting to q square by 2 c in charging the capacitor, and it is this work done that is stored as electrostatic energy within the capacitor. So, energy stored is equal to u is equal to q square by 2 c. So, this is while charging the capacitor I am doing work, and that work which I am doing is stored as electrostatic energy in the capacitor. This formula is very similar to the energy potential energy stored in a spring mass system. So, if I have a mass connected to a spring with spring constant k, remember that the energy stored in pulling the string by an extension x is half k x square. So, the displacement plays the role of the charge here, and k is something like 1 by c in this equation. So, just like a pulled spring stores energy, a charged capacitor stores energy, and that is the energy stored in the capacitor. Now, using the relationship q is equal to Cv, I can write the energy stored in another form. So, q square by 2 c, which is equal to 1 by 2 c, q is equal to Cv. So, this is c square v square, which is equal to half c v square. That is another form of electrostatic energy. I can also write it in a different form. I replace only one of the q by Cv, so which is equal to half qv. So, there are three forms of energy. I can have energy is equal to q square by 2 c, or energy is equal to half Cv square, or energy equal to half qv. All of them are equivalent, and we can use any of them at any given time. Depending on the problem, I will use one of these equations to calculate the energy stored. Now, I can actually calculate, I can put this energy in a slightly different form by taking the example of a parallel plate capacitor. So, remember, in a parallel plate capacitor having an area A and a separation d, suppose this is positive charge here and there is negative charge here, there are electric field lines coming downwards, and so the energy stored is q square by 2 c, or equal to half c v square. Now, c is equal to epsilon 0 a by d, we have already calculated, and v is equal to E times d. So, I can put u is equal to half epsilon 0 a by d into E square into d square. E is the electric field between the capacitor plates, and so this is equal to half epsilon 0 E square into a times d. So, I write it in this form, separate the factors into two parts, half epsilon 0 E square into 1 d cancels off and I get a times d. Now, what is a times d? This is volume enclosed. So, if I look at this energy, I can interpret this equation by saying that the energy is stored in the form of an electrostatic field, and the energy density or the energy per unit volume stored in the electrostatic field is given by half epsilon 0 E square. This is the volume of the capacitor, and that is the, so if I multiply this quantity by the volume, I get the total energy. So, this must be the energy per unit volume. So, if I have an electric field inside the between the capacitor plates, I have an electric field E, and I find that I can interpret this equation as if half epsilon 0 E square is the energy per unit volume stored in an electrostatic field. Although I have derived this equation for a parallel plate capacitor, this is a very general equation, and so if you have an electric field E at any point, the electrostatic energy that is contained in that electric field is half epsilon 0 E square if it is free space. So, that is the energy density, and this is a nice way of interpreting this electrostatic energy. Now, although I have derived that for a parallel plate capacitor, I want to take an example, another example, and to show that this equation will also be working correctly. So, I take a spherical capacitor. So, remember I had a spherical capacitor, there was a conductor here and there is another conductor outside. So, R A is the radius of this conductor and R B is the radius of that conductor. So, let me draw charges here. So, I had plus charges here and I have minus charges in the outside. So, the outside conductor is a finite thickness conductor. So, we have already calculated the capacitance of this. Capacitance of the spherical capacitor is 4 pi epsilon 0 R A R B by R B minus R A. In an earlier class, we had calculated the capacitance of a spherical capacitor as C is equal to 4 pi epsilon 0 R A R B by R B minus R A. So, the energy stored U is equal to 1 by 2 q square by C, which is equal to q square by 8 pi epsilon 0 R A R B into R B minus R A. So, using the formula q square by 2 C, I get an expression for the energy stored in a spherical capacitor as q square by 8 pi epsilon 0 R B minus R A by R A R B. So, that is one way of calculating. Now, let me calculate the energy stored in the electric field which lies between the two conductors and show you that if I assume the electrostatic energy density is as half epsilon 0 E square, I will get the same expression for the total energy stored. So, let me redraw the capacitor again. So, I have the inner conductor here and the outer conductor. So, inner conductor is positively charged. So, I have positive charges here and the outer conductor has negative charges. Now, so to calculate, so energy density I know is equal to half epsilon 0 E square. Now, first, so for this, to use this I must calculate the electric field at different points. So, first thing, remember that this is a conductor here, that is a conductor. So, the entire electric field in this configuration lies between the distance R A and R B. There is no electric field within this conductor, there is no electric field within this conductor, there is no electric field anywhere else except in the region between R A and R B. And to calculate this, I must know the electric field. So, what we have done before is exactly like this. So, I take a Gaussian surface of radius r and calculate that flux crossing this. So, flux crossing is 4 pi r square into E, which because E is radial and so the flux crossing the spherical surface is 4 pi r square into E, which is equal to charge enclosed by epsilon 0. So, E is equal to q by 4 pi epsilon 0 r square. So, we have seen this before. This particular spherical charge distribution actually is equivalent to a point charge situated at the center of the sphere, that is the electric field. And please now note that the electric field depends on the position. In a planar, in a parallel plate capacitor, the electric field was uniform, here the electric field depends on position. So, I just cannot multiply this number by the volume, I must integrate. So, what I do is I take, so this is my inner conductor here. So, I take a surface lying between R, a volume lying between R and R plus dr. So, this is R plus dr. So, in this volume I want to calculate the energy and then I will integrate over the entire distance from R A to R B. So, what is the energy contained in the volume between R and R plus dr? The energy density of epsilon 0 E square, which is q square by 4 pi epsilon 0 whole square R raised per 4 E square into the volume of this, which is 4 pi r square into dr. The area of the sphere into the thickness, which is 4 pi r square dr. So, this gives me equal to q square by, now 1 4 pi epsilon 0 cancels off and I get 8 pi epsilon 0 into dr by r square. So, 1 r square cancels off and I get q square by 8 pi epsilon 0 dr by r square. So, as you can see the energy stored changes with position because the electric field is strong here. So, there is more energy density, the electric field is weaker, gets weaker as you go away from the center and the energy density keeps on decreasing. So, that is energy density, energy lying between r and r plus dr. So, the total energy, total stored energy U is equal to integral r a to r b q square by 8 pi epsilon 0 dr by r square, which is equal to q square by 8 pi epsilon 0 into 1 by r a minus 1 by r b, which is equal to q square into r b minus r a by 8 pi epsilon 0 r a r b. And if you compare this with the expression that we had just now obtained from the other equation, you see this equation here, they are the same equation, q square by 8 pi epsilon 0 into r b minus r a by r a r b. So, please note that either of the formulations gives me the same total energy contained. In this case I had to be a little careful because the electric field is not uniform. So, the energy density stored in the electric field, electrostatic field changes with position. So, when I calculate in such a case, I must calculate the electric field at different points and then I will get the energy density at different points and then I have to integrate over the entire volume where the electrostatic field exists. So, these are two ways of calculating and this tells me that energy is stored in the in an electrostatic field. And so, when a capacitor is charged, I store electrostatic energy and that energy can be discharged at any later time from the capacitor and so the capacitor does work and releases that energy. Now, I want to discuss something about dielectrics and polarization. Remember we had discussed dielectrics are those materials in which there are no free electrons. So, the unlike conductors, in conductors there are free electrons, the outermost electrons of the atoms are free from the atom and they are free to move anywhere within the conductor. So, when you put a conductor in an electric field, the electric field then applies the force on these charges on these electrons which then move because of the electric field and they continue to move until the electric field within the conductor becomes 0. So, we have seen that in the static case there cannot be any electric field within the conductor. Now, in a dielectric there are no free electrons, but there are atoms which contain charges. So, usually as we have discussed before, the center of the negative charge of the electron cloud surrounding the nucleus and the center of the positive charge of the nucleus are coincident at the same point. So, you do not see any electric field from the atom, but when you put an atom in an electric field, the atom gets polarized. So, what happens is you may start with an atom with a positive and negative charge which are coincident at the center. So, when you apply an electric field like this, then what happens is you have a small separation of negative and positive charges and this forms a dipole. We have seen this is a dipole and it is characterized by dipole moment. So, when you place a dielectric within an electric field, the atoms get polarized and we say that the dielectric gets polarized in this process. So, we will call such a dielectric to be a polarized dielectric. So, placing a dielectric within an electric field immediately polarizes the dielectric. So, now first let me see what happens if I had a uniform electric field and I had a block of conductor. So, I had a conducting block here and I had an electric field in this direction, a uniform electric field. For example, I place this conductor between the plates of a parallel plate capacitor. So, I have this conductor. Now, the moment I apply an electric field on the conductor, inside the conductor there is instantaneously some electric field. That electric field now will move the electrons and the electrons will get accumulated on one side, leaving a net positive charge on the other side. So, you will have electrons attracted here to this side and there will be net positive charge on the other side of the conductor. We have seen this before. So, this leaves a surface charge density on the conductor and the charges will continue to move until the net electric field within the conductor becomes 0. So, if the electric field which I have applied is E naught and if sigma is the surface charge density here, the electric field because of these two surface charge densities is sigma by epsilon 0 and that must be equal to E naught. So, E naught is like this and the electric field because of the surface charge is like this and they must be equal to cancel the electric field here. So, I generate a surface charge density which is epsilon 0 is 0. So, this surface charge density gets created which creates its own electric field. So, the electric field within the conductor becomes 0. That is the story of a conductor. Now, what happens if I place a dielectric inside an electric field? So, let me take a dielectric now. So, I have a dielectric and I again have a uniform electric field applied in this upward direction. Now, as we have seen in the absence of electric field there are atoms within the dielectric whose positive and negative charges coincide. The moment an electric field is applied the negative charges get attracted and I will schematically draw each of these atoms as a oval shaped object here. This is essentially denoting each of the dipoles which is formed because of the application of the electric field and I know that the charges will be plus on the upper side and minus on the lower side. So, the electrons get attracted in the downward direction because of the upward electric field leaving a net positive charge. So, there are each atom becomes a dipole with the dipoles pointing upwards. So, remember the dipole moment of a dipole is a vector joining the minus to the plus charge. So, these are all dipoles small dipoles which have the dipole moments pointing upwards. Now, so I have just drawn some atom there are billions of atoms in the dielectric. So, this dielectric gets polarized this is supposed to be a polarized dielectric. Now, you can see if you take any small volume within the dielectric, volume is small compared to the size of the dielectric the transfer size of the dielectric, but large compared to the atomic spacing. You can see that there will be an equal number of positive and negative charges within that volume. So, effectively there is no volume charge density created within the dielectric. But look at the surface here there are negative charges left which are not compensated by positive charges. Similarly, there are positive charges left on the upper surface which are not compensated by the negative charges. So, the moment I put a dielectric in an electric field, the atoms get polarized, each atom becomes a small dipole moment and you are left with a surface charge density on the lower side, negative surface charge density on this side and a positive surface charge density on this side. So, the result of polarizing a dielectric is to leave surface charge density on both surfaces in this diagram, this particular surface and this particular surface. So, this dipole now will create its own electric field. So, there are charges negative charges on the lower surface, positive charges net charges on the upper surface that produces a downward looking electric field which partially cancels this electric field. In a conductor the downward directed electric field is equal to the upward directed applied electric field resulting in a complete cancellation. In the dielectric case, as you will see, the cancellation is partial. So, let me assume that in the dielectric I am left with a positive charge on the upper surface. So, the upper surface has a net positive charge and the lower surface has a net negative charge, and there is no other volume charge density inside. So, I have an uniform electric field. So, this results in what I will call as bound surface charge density. So, sigma b and minus sigma b. Sigma b is the bound surface charge density. It is called bound surface charge density because these electrons are not freed from the atom, they are still attached to the atom. Only thing that has happened is they have got a little stretched. The center of the negative charge has got displaced with respect to the center of the positive charge, with the result that each atom becomes a dipole, and when this dielectric gets polarized, it results in a bound surface charge density on these two surfaces, and we say that the dielectric is polarized. And to quantify this polarization, we define a vector called polarization. Which is denoted by P. This is the dipole moment per unit volume. So, you take a small unit volume or you take a small volume delta V, calculate the total dipole moment of delta V and divide the dipole moment by the delta V to get the polarization of the dielectric, and this polarization is caused by the external electric field. So, inside the dielectric there is an electric field E and there results a polarization P. So, this polarization vector must be proportional to the electric field applied, and so we have a relationship like this epsilon 0 chi E. This is epsilon 0 is the permittivity of free space and chi is called the electric susceptibility. It measures how much susceptible is the dielectric to polarization. So, that is a susceptibility. So, P is called the polarization and it is related is proportional to the electric field. Now, this relation is true for small electric fields, and if your electric fields become very strong, then this equation breaks down and we need to modify this equation, but we will not discuss that here. For small electric fields which are usually found, polarization of the dielectric is proportional to the electric field, and as this vector relationship shows that P and E are in the same direction. Now, so let me calculate. So, how do I relate polarization to the surface charge density? So, we have shown that there is a bound surface charge density and this bound surface charge density comes because of polarization. So, how is this P related to the surface charge density? So, to calculate this, what I do is the following. I take a cylinder, a small cylinder of length L, area A, and polarize like this. So, let me assume that the two ends of the cylinder are at right angles to the polarization. The polarization is along the length of the cylinder and the polarization in the dielectric is equal to P. So, let me write a scalar relationship. I know it is along this direction. So, the polarization is P and volume is A times L. So, the dipole moment of this cylinder is P times A times L. P is the dipole moment per unit volume, A times L is the volume of the dielectric, A surface area multiplied by the length, and P times A times L is the dipole moment of this cylinder. Now, I can also write this dipole moment in a slightly different form. Let me assume the charges are Q minus Q and plus Q here. So, if I have two charges plus Q and minus Q separated by length L, I can write the dipole moment as Q times L. So, this implies that Q times L is equal to P times A times L, or Q is equal to P times A. So, Q is the charge accumulated on this side plus Q minus Q and the surface area is A. So, I can get the bound surface charge density sigma B is equal to Q by A, which is equal to P. So, when I look at the cylindrical object which is polarized along the axis of the cylinder, I find that the surface charge density here, bound surface charge density on both sides is minus sigma b and plus sigma b. So, the bound surface charge density is related to polarization like this, and in this example I have assumed that the end surface is perpendicular to the polarization vector. Now, you may not have always the same situation, you may have surfaces which are not perpendicular to the polarization. To find out what happens in a situation like this, so let me draw the same cylinder here now. Now, the surface happens to be at an angle. So, let me assume that this angle is theta, the polarization is still like this, theta is the angle, theta is the angle made between this inclined surface, inclined area and this normal. So, I can define, as we have defined before, a unit normal along the area, and polarization vector is like this, and this is theta. Now, please remember, just like before, the charges which are accumulating here is minus q, and on the surface is also plus q. The same charge gets accumulated on the other surface. Now, the area instead of being A is A by cos theta. This area is larger than this area is perpendicular area, that is an inclined area. So, if an inclined area, that area is larger than this area A, and it is A by cos theta. So, the bound charge density now becomes sigma b is equal to q by A by cos theta, which is equal to p cos theta, because q by A is sigma p into cos theta, which is equal to p dot n. P vector is like this, n vector is the normal to the surface, is outward normal. The surface, the volume of the dielectric is here, n cap is the outward normal, and p cos theta is nothing but p dot n. So, this is a specialized relation when p and n are parallel, but in general if you have a surface in which is on the one side of which is the dielectric with a polarization p, it creates a surface charge density, bound surface charge density of p dot n. So, you can see in this example on the left side, this side n vector is like this, n cap, and p vector on this is like this. So, p dot n is minus. So, you have a minus charge density here. On this surface, cylindrical surface, n cap is like this, p is like this, and p dot n is 0. So, there are no surface charge densities on the cylindrical surface, because that is parallel to the p vector, and the normal to the surface is perpendicular to p vector, and p dot n becomes 0. On this surface, which is inclined at an angle theta, the surface bound surface charge density is p dot n, which is sigma b. So, that is a very general relationship. Whenever you have a polarization p in a dielectric, it creates a bound surface charge density of p dot n. So, this relationship is useful for us to analyze dielectrics, electrostatics with dielectrics. So, now I want to calculate the capacitor with a capacitor with a dielectric. In all our earlier discussions, we assumed that the capacitor plates have no they are just spaced, and there is air or vacuum in between. We did not consider any medium to be present within the plates of the capacitor. Now, I want to have a capacitor in which I am going to assume that there is a dielectric kept filling the entire space. So, I have a dielectric here filling the entire space of between the parallel plate capacitor. So, again let me draw positive charges here, and there will be negative charges on the plate here. So, there is an electric field in the downward direction. So, this will result in a negative accumulation of negative bound charge here and an accumulation of positive bound charge here. So, let me write here. So, this is plus sigma f, this is minus sigma f, this is minus sigma b, and this is plus sigma b. On the surface of the dielectric, we have bound surface charge densities, which I am calling minus sigma b and plus sigma b, on the surface of the conductors we have free charges which are plus sigma f and minus sigma f. Now, I want to calculate what is the electric field within the dielectric. So, we follow the same procedure as before, we use Gauss's law. So, I take a Gaussian surface like this, I take a Gaussian cylindrical surface with an area A and in the vertical direction. Now, you can see here because of the symmetry of the problem, the electric field will be downwards. There is an electric field created by the charges plus and minus on the conducting plates which is acting downwards. There is a electric field created by the dielectric, polarized dielectric which is upwards, but as we have seen before this we will see that this cancellation is not perfect. So, there is some electric field still left within the dielectric, unlike a conductor where the electric field should be 0, there is no such condition for dielectrics. So, the electric field lines are like this. So, this is the Gaussian surface, there is no electric field within the conductor. So, the flux on the surface is 0. This cylindrical surface of the Gaussian surface is parallel to the electric field. So, there is no flux on that, there is only a flux from here. So, if E is the electric field, E into A which is the flux must be equal to the charge enclosed. Now, the charge enclosed has two components, free charges here and bound charges here. So, the total charge is sigma f minus sigma b into area, because that is the surface charge density, and see this is the surface charge density multiplied by area of the charge divided by epsilon 0. So, that is Gauss's law. The electric flux through any closed surface is equal to charge enclosed by epsilon 0, and that is what I am using here. So, A cancels off and I get epsilon 0 A is equal to epsilon 0 E is equal to sigma f minus sigma b. Now, sigma b we have just now shown, sigma b in this case will be p which is equal to epsilon 0 chi e. So, I have epsilon 0 e plus sigma b which is epsilon 0 chi e is equal to sigma f. So, this implies epsilon 0 into 1 plus chi into E is equal to sigma f. So, chi is the susceptibility. So, we define new quantities now. I define dielectric constant K as 1 plus chi, and then I have permittivity of the dielectric epsilon is equal to epsilon 0 into 1 plus chi which is equal to epsilon 0 into k. Epsilon 0 is the permittivity of free space, epsilon is the permittivity of the medium of the dielectric, and so epsilon is equal to epsilon 0 times k, and k is usually greater than or equal to 1. K is equal to 1 for free space or vacuum, and k is always more than 1. So, if I go back to this equation, I get the electric field in the dielectric as E is equal to sigma f by epsilon 0 k which is equal to sigma f by epsilon. And you can see here that because k is more than 1, this electric field is smaller than the electric field when there was no dielectric placed within the plates of the conductor, between the plates. So, the electric field within the dielectric actually is smaller than the electric field which was created in free space, and this the reduction is by a factor k which is the dielectric constant of the dielectric. So, let me take an example here. So, before that I will give you some values of dielectric constants of standard materials which are used in various capacitors. So, I have a table here, material and K. So, Pyrex glass is a type of glass 4.7, polystyrene which is 2.6, paper is 3.5, porcelain which is 6.5, titania ceramic (130). So, there are dielectrics with very strong permittivities, strontium titanate, which is even larger, 310, and it is interesting to know the dielectric constant of water, which is 80.4. So, these are some dielectric constants of some dielectrics which are used either in capacitors, or otherwise we should know some of the numbers, and we can see here there is a wide variety of dielectrics with dielectric constants varying right from almost close to 1. In fact, air at the dielectric constant which is very, very close to 1, slightly more than 1, very close to 1, right up to couple of hundreds. So, it is a very wide range of materials, and depending on the kind of capacitance I need, I can use different dielectrics for the capacitance. So, let me take an example here. Okay, so, we have calculated this electric field as E is equal to sigma f by epsilon. So, let me go back and look at what is the capacitance of this capacitor now. So, I have the dielectric filling the space between the. So, electric field becomes sigma f by epsilon. Now, sigma f is equal to q by A is the area of the plates, and E is equal to potential difference divided by the separation. So, V by D is equal to q by A epsilon. This implies V is equal to q into D by A epsilon. So, we know the capacitance is given by q is equal to C V, q is equal to C times V. So, the capacitance of this capacitor with the dielectric filling C is equal to, so C is q by V, which is epsilon A by D. Remember, when the space between the parallel plates was filled with free space, the capacitance was epsilon 0 A by D. Now, the capacitance is epsilon A by D, which is actually epsilon 0 K A by D, because epsilon, the permittivity of the dielectric is epsilon 0 times the dielectric constant. So, the capacitance has increased by a factor K. So, as an example, let me take so here is an example. So, area of plates 100 centimeter square, and spacing between the plates is 1 centimeter. So, with air, first air separating the plates, epsilon is equal to epsilon 0 approximately, and you can calculate the capacitance. C air is equal to epsilon 0 A by D, which comes out to be 8.85 picofarads. If you put a dielectric, and dielectric constant is 2.6, then the capacitance with the dielectric becomes about 23.01 picofarad. So, there is an increase in capacitance by the factor the dielectric constant K, and the capacitance increases by filling the capacitor with dielectrics. So, actually if you want to have a higher capacitance, we can use dielectrics to fill and increase the capacitance. Let me try to clarify further here. So, let me take for example the same capacitor, but instead of filling the entire space with the dielectric, suppose I had dielectric only partially filling, and I had positive charges here, negative charges on the lower plate of the conductor. So, these are the two conducting plates. So, this induces a negative bound charge here, and that induces a positive bound charge here and negative bound charge on this side. So, you have an electric field pointing downward here, and also pointing downward here, but slightly weaker. So, you can actually calculate the electric field in this space E A. So, if I call this sigma f and this is sigma b, E A is equal to sigma f by epsilon 0, and if the dielectric constant of this is K, the sigma E dielectric is equal to sigma f by epsilon 0 times K, which is equal to sigma f by epsilon. And you can see that E A is greater than E of the dielectric. So, what the dielectric does is gets polarized. A polarized dielectric creates an electric field in the opposite direction as the applied electric field, and there is a partial cancellation. In a conductor, this cancellation is complete, while in a dielectric the cancellation is only partial. Okay, so we can look at various examples, but before I do that, I would like to discuss a very important issue, which is Gauss's law in dielectrics. Till now we have discussed Gauss's law with no medium in between. So, we had a charge, surface charge density for example, or a conductor which is charged, or a point charge, set of point charges, all in free space, and we never took in account of any medium. Now, I want to find out what happens to Gauss's law in the presence of a dielectric. So, to understand what happens, let me consider the following situation. I have this is the conductor and this is the dielectric. This is a conductor and this is the dielectric. So, let me assume there are positive charges on the surface of the conductor. This will lead to a bound surface charge density on the surface of the conductor. So, this is sigma f and this is sigma b. Free charges on the surface of the conductor here and bound charges on the surface of the dielectric. So, let me take a Gaussian surface like this, and assuming this to be flat plane surfaces, the electric field lines are perpendicular to this interface. There is no electric field on this surface because it is inside the conductor. There is no electric field crossing these surfaces because electric field lines are parallel to this curved surface. The only electric field crossing is on this surface. So, if the surface area is A, I will write E times A is equal to, just like before, sigma f minus sigma b, the net charge multiplied by A by epsilon 0. So, electric field crossing this entire surface, Gaussian surface, is E times A because there is no electric field here. This line, there is no crossing, there is no flux on the surface, the only flux is from the surface within the dielectric. So, I will write this as epsilon 0 E plus sigma b is equal to sigma f, and sigma b I know is nothing but p. So, I write this as epsilon 0 E plus p is equal to sigma f. Now, there is a name given to this vector, it is called the displacement vector. D vector is equal to epsilon 0 E plus p. So, this is a scalar relationship, but if I look at it in a vector form, this is a displacement vector. So, this equation becomes nothing but D is equal to sigma f. Now, I can multiply both sides by area and write this as sigma f into A. Now, what is I can interpret D times A as the flux of the displacement vector through the same Gaussian surface. What this was the flux of the electric field through the Gaussian surface, D times A I can interpret as the flux of the displacement vector on the same Gaussian surface. So, I get that the flux of the displacement vector is equal to total free charge enclosed by the surface. This was free charge, the total charge including free and bound charges. Here I get displacement flux of the displacement vector is equal to the free charge enclosed. So, I get this equation. I can write this in an integral form as the following: integral d dot dA is equal to free charge enclosed. The Gauss's law for electric fields was integral E dot dA is equal to total charge enclosed by epsilon 0. Here for the displacement vector, this is the Gauss's law. I can also write this as epsilon E dot dA is equal to free charge enclosed. Please remember that on this, in this equation, in this Gauss's law form, the charge on the right hand side is only the free charge, and that is all that I needed to know to find out what is the displacement vector, and from the displacement vector I can use this equation to calculate the electric field vector. Now let me take one example of Gauss's law in a dielectric. So let me assume that I have a conductor of radius A surrounded by a dielectric of radius B. This is a conductor, and let me assume that the charge, there is a charge q on this, q, and this is the dielectric. Now because of this spherical symmetry, the electric field lines will be radial, the displacement vector lines will be radial. So I take a Gaussian surface of radius r. So I use this equation d dot dA is equal to free charge enclosed. Because the displacement vector is perpendicular to the surface, this tells me simply d times 4 pi r square is equal to q. Q is the surface charge enclosed, the charge enclosed. Please remember there is a dielectric here. So if I were to draw the charges, if the dielectric has positive charge, there will be negative bound charges on this side, but I am not bothered about the bound charges at all in using this form of Gauss's law, because it only requires knowledge of free charges. So displacement vector is actually q by 4 pi r square. In fact, no matter what value of r you take, whether within the dielectric or outside the dielectric, this is the displacement vector. So for r less than b, greater than a but less than b, the displacement is equal to q by 4 pi r square, and this is equal to epsilon E, because there is a dielectric with permittivity epsilon. So E will be equal to q by 4 pi epsilon r square. For r greater than a, for r greater than b, T is again given by q by 4 pi r square, but now in this case d is epsilon 0 E. So the electric field in this case will be q by 4 pi epsilon 0 r square. So you see what I have got is, using this form of Gauss's law, I have been able to calculate what is the electric field in a situation like this. So once I know the electric field in all the regions, I can use this electric field in the expression for polarization to calculate the polarization. Once I know the polarization, I can calculate the surface charge density. So this is a very, very powerful form of Gauss's law with using dielectric, with using displacement vector, and is applicable whether you have dielectrics or not, and this is very useful especially in situations where there is symmetry. So I would like to summarize what we have been doing in electrostatics. We started with Coulomb's law, then we introduced the principle of superposition, where we calculated the total electric field by a number of charges, and then with that we also introduced the concept of electric field lines, and then we specifically calculated the electric field due to a dipole, and also calculated what are the forces and torques on dipoles, and then we introduced the very important principle of Gauss's law and used that Gauss's law to calculate electric fields in different symmetric situations. We introduced the concept of Gauss of flux, electric flux, and then we also discussed conductors, equipotential surfaces, electrostatic potential energy and electrostatic potential, and finally we discussed some capacitors and capacitance, and also dielectrics inside capacitors and how the electric fields get modified. And finally we just introduced Gauss's law in a dielectric, and these are very general principles of great application in the field of electromagnetics. Thank you very much.